Alright, in this third lesson, we'll take a look at oxidation-reduction reactions. Now this is a class of reactions that you have not yet seen in Chemistry 1, so most likely this will be new. You've seen these types of reactions, but we've never thought of them as oxidation-reduction. And by oxidation reduction, what we mean is a reaction in which there is a transfer of electrons between species. If you take a look, for example, magnesium, as you'll see here, will give up its electrons to hydrogen, and hydrogen will accept those electrons, and then hydrogen then will become by itself. You're used to this as being a single replacement reaction. We're going to define it as an oxidation reduction reaction. So quickly we're going to define oxidation and reduction. Oxidation means that an atom or molecule becomes more positively charged. And oxidation by definition is the loss of electrons. So if a substance gets oxidized, what happens, say for example magnesium goes from magnesium metal to magnesium 2+. This is actually called oxidation, going up in charge. And then reduction, on the other hand, is the opposite. It's whenever a molecule, atom, or ion becomes less positively charged. So think reduction, reducing in charge. And it reduces in charge because it gains electrons. So if you take a look, if say magnesium were to go from +2 down to regular magnesium, being the opposite, this means magnesium will have to receive electrons to get rid of this +2 charge. This is what we mean. And here's a quick way of remembering it. This acronym oil RIG. So oxidation is losing electrons, and reduction is gaining electrons. So reduction, recall, is whenever you go down in charge while electrons are negative. So when you receive electrons, you will go down in charge. Here's another example. So in this case, this is just a famous reaction of hydrogen and oxygen reacting to form water. If you analyze hydrogen before and after, what you would see is that hydrogen actually lost electrons, which means it got oxidized. And oxygen, on the other hand, gained electrons, so it became reduced. And the reason why we call it oxidation, historically, oxidation actually means that it reacted with oxygen, and oxygen, being very electronegative, stole its electrons. So the substance got oxidized, and this will make more sense, I think, as we go on here. So we're going to have to take a look at something called oxidation numbers. This is the actual or assigned charge of an atom. So we're actually going to assign oxidation numbers or charges to atoms. And this is essentially what we're doing here. So, and this helps us keep track of the electrons, so we can take a look at what happens in the chemical reaction. So here are a few rules. Anytime an atom is in its elemental form, which means it's an element, the oxidation number by definition is 0. So what you see here, oxygen down here is elemental oxygen, which is diatomic. Its charge is 0. Magnesium, being elemental metallic magnesium, has a charge of, or an oxidation number of 0. Monatomic ions will have, its charge will be simply its oxidation number. So here chloride has a -1 charge, so its oxidation number is -1. Calcium has a +2 charge, its oxidation number is +2. And there's a reason actually why we don't call, we call these charges, but we differentiate that and oxidation number. And you'll see that oxidation number oftentimes is hidden within a compound, and you'll see that next. So in general, when in a compound, oxygen will have a -2 oxidation number, except in something called peroxide, and this is actually part of the, I believe it was part of the summer homework, where oxygen could have a -1 charge, and it'll be teamed up with itself, as in hydrogen peroxide. The famous compound here is actually hydrogen peroxide, H2O2. And as you'll see, since there are two hydrogens, each being a +1 charge, you'll require each oxygen to be a -1 charge for this thing to be neutral. So hydrogen has a +1 charge, usually when bonded to nonmetals, like in the case of water, or like in the case of hydrogen peroxide. and then it'll have a -1 charge when bonded to metals. Now these are much more rare, but you could have, for example, sodium hydride. This is an actual compound, and in this case, because hydrogen is bonded with a metal, sodium, it'll have a -1 charge. Halogens, being from group 17, in binary compounds, binary meaning all you have is a halogen and another metal, which in this case, like halogen and iron, you'll have yourself a -1 charge on halogen, on chloride. Rule number 3, this is where it's going to get a bit tricky. So for polyatomic ions, we have to take a look and do some accounting to find out the oxidation number. The way we're going to do this is we'll assume oxygen is -2. And then the sum of the oxidation numbers will give you the charge of the polyatomic ion. So, in other words, sulfur and 3 oxygens summed up will give you a -2 charge. And then if you have a compound, then the sum of all of these atoms, or ions in this case, will be 0, because a compound by definition is neutral, so it has a charge of 0. So let's take a look at this. We're going to try to determine the oxidation state of sulfur in each one of these. So let's begin with S8. So with S8, now it's if you're wondering why there's 8 sulfurs bonded together, this is a common form of sulfur, of elemental sulfur. It'll actually form a ring. Sulfur will form kind of an 8-sided ring with itself, and there are essentially 8 atoms of sulfur in this ring. So that's why there's an 8 at the bottom. But because it's elemental, all elements have an oxidation number of 0. Alright, let's take a look at H2S. This is hydrogen sulfide, or if you like, dihydrogen sulfide. If you take a look here, since we said that each hydrogen has a +1 charge, we have 2 +1s, 2 hydrogen ions, and so sulfur must have a, to balance that out, since this compound is neutral, must have a -2 oxidation number. So in the second case, sulfur has a -2 oxidation number. In the first case, it was 0. If you take a look at SCl2, chlorides, being a halogen, chlorides are usually -1 from the periodic table. You got 2 chlorides here, so sulfur therefore must be a +2 charge to counteract those 2 -1s. So here you have a +2 in this compound. And really we can do this. We can actually put a little +2 circled. Here we can put -2 circled. Thirdly, we got ourselves a sulfate polyatomic ion with a -2 charge. So here we have to consider oxygen. So because each oxygen has a -2 charge, and we have 4 of these oxygens, let's think about the oxygen side here. You got 4 -2s. So each oxygen is -2, you got 4 of them. And this gives you a total of -8 from the oxygens. Now the overall compound has a charge of -2. And the question is, what must sulfur be so that sulfur -8 gives you -2? And sulfur then must be +6, because +6 -8 gives you -2. And the idea here is that, recall that the total sum of the oxidation numbers has to give you the charge of the polyatomic ion. So sulfur here actually has a +6 oxidation number. And finally, if we take a similar look at sodium, in this case it's sodium sulfite, SO3. So we got sodium. Sodium is actually a +1 charge. We got 2 of them. So we have 2 +1s. Each one of these is +1, and we got 2 of them. So we have a +2 total from the sodium side. If we take a look at the oxygens, again each oxygen is a -2, and we got 3 of them. So the total oxidation number from the oxygens will be -6. Now the overall charge, because this is a compound, is neutral, so this whole thing equals 0. And the question is, plus 2, what must sulfur be so that plus 2 plus sulfur minus 6 gives you 0? In this case, sulfur must be plus 4, because plus 2 plus 4 gives you 6, minus 6 gives you 0. So sulfur here has a plus 4 charge, or plus 4 oxidation number 2. So to review, in S8, sulfur had a oxidation number of 0, in H2S, an oxidation number of minus 2, in SCl2, a plus 2, and in this case, in SO4, plus 6, and in sodium sulfite, plus 4. So what you could see is that sulfur has 5 different possible oxidation numbers. It actually has more than 5, but this is different. We've seen from Chemistry 1 that we're used to sulfur having a minus 2 charge, but here oxidation number is different than charge. So we can assume, or we can actually arrive at different oxidation numbers for sulfur. This is a little different, quite a bit different from what we've seen in Chemistry 1. Okay, so we're going to show some reactions now. So here we have metals will be oxidized by acids to form salts. Recall that oxidized just means they're going to go up in charge by losing electrons. So magnesium, being by itself here, has a 0 charge. Magnesium being with 2 chlorides has a plus 2 charge. So you see actually magnesium being oxidized from left to right. And it's oxidized by hydrochloric acid. And they can also be oxidized by other salts. So what you will recall, these are actually single replacement reactions from Chemistry 1. And a single replacement reaction is actually an oxidation reduction reaction. So here, a similar thing happens. Iron will actually go from a 0 charge to a plus 2 charge, again, being oxidized, and they'll do so by giving up electrons to nickel. Nickel will accept those electrons, and it will be reduced. So we'll go from a plus 2, in this case, to a 0 on the right side. And then it's a little more clearly seen in this slide. So essentially, just a review of exactly what we saw upstairs. So magnesium being 0 and plus 2, that means it got oxidized. Hydrogen being plus 1 here and 0 here because it's elemental, has a 0 charge. Hydrogen got reduced. And you'll always have, this will always be the case. Anytime one substance is oxidized, the other substance must be reduced, because whatever's getting oxidized is giving up electrons, and something else must accept those electrons. Okay, so here we have another example. This will be a bit involved, but we've done this a few times now. This is going to be the same thing we've done for both the precipitation and acid-base reactions, except now we'll do it for an oxidation-reduction reaction. Write the balanced molecular and net ionic equations for the reaction of aluminum with hydrobromic acid, and what element is oxidized in the reaction. So let's give this a whirl. Let's begin with the molecular equation. So we have aluminum, which is simply written as Al, with hydrobromic acid. If you recall, hydrobromic acid is kind of like hydrochloric, so it's just HBr. So think of this then as a single replacement reaction. Aluminum will come in and replace the hydrogen. So once aluminum replaces the hydrogen, because aluminum has a plus 3 charge, bromine has a minus 1 charge, we've done this already, so our compound should be written as AlBr3. And then what is left is hydrogen. Recall that hydrogen is diatomic, which means you got yourself H2. Let's go and balance this equation. So since we have 2 hydrogens here and 1 hydrogen here, why don't we do, I'll go ahead and double this up to keep it nice and even. So this gives us 6 bromides, or bromines, and that we'll have to put a 6 in front of here to balance that. That gets us 6 hydrogens, so 3 in front of here gets us 6 hydrogens, and don't forget the 2 to balance the aluminum. And then lastly, we want to include the state symbols, because when we write the net ionic equation, we'll have to be able to cancel out a lot of these. So aluminum being elemental is a solid. HBr is going to be aqueous, and the way to remember this, all acids, technically all acids are aqueous. This is because an acid actually is usually a gas dissolved in water. So all acids by definition will be aqueous. That's a good thing to remember. Aluminum bromide since it's soluble, will be aqueous, and it's soluble because it's got a halogen with aluminum is not a robber, therefore it is soluble, and hydrogen is actually a gas. So what we'll do is exactly the same thing we've done before. Let's go ahead and rewrite everything that's aqueous. Let's separate it into ions. So aluminum stays as it is. HBr separates into H plus and Br minus. Aluminum bromide does the same thing, separates into aluminum plus 3 and Br minus. And then hydrogen stays as it is. And now we'll cross out anything that appears the same on both sides. Now in this case what you'll see is aluminum on the left side and on the right side changed. In fact, aluminum here is elemental, has a 0 charge. Here aluminum has a plus 3 charge, so it did change. So we cannot cross it out. The bromides really are the only ones that didn't change, so we will cross them out. And then we'll bring everything else down, and we'll complete our reaction. So essentially we got aluminum with hydrogen ion producing aluminum 3 plus and hydrogen gas. And again, if you want to see what happens, you'll see that aluminum went from 0 to plus 3, got oxidized. Hydrogen went from a plus 1 to 0, got reduced. So you can kind of see the oxidation reduction idea here. Let's go ahead and balance the equation. And you can always look up at the original equation to help you balance it. Since we had a 2 in front of the aluminum up here, right up here, and we'll just kind of take these numbers down. You can balance it on its own, or you can, if you balance the initial one, you can actually just take the numbers down, and that will work. To put it 2, 3, and 3 here. In fact, if you account for it, we got 2 aluminums, 6 hydrogens, that works. So this one should work. Then finally, let's go ahead and put the state symbols in. Customarily, oftentimes we'll put state symbols, and again you can just take them down from the molecular equation up there. Aqueous here, and we got hydrogen gas, and this is your net ionic equation. This really is what we finish up with, because this really tells us what's happening. The net ionic equation is the big dog here that we want to look at. Alright? And that's a bit messy, isn't it? Lastly, we're going to finish up with something called the activity series. Now, you should have seen the activity series in Chemistry 1. If you did not, we'll go through it here. And the activity series is simply a list of metals for single replacement reactions. And it's in decreasing ease of oxidation. Now, that's confusing, and I'll try to explain it in a different way. But the higher the metal on these series, the more active that metal. So on top, you'll find very active metals, on the bottom, not so active. Here it says any metal can be oxidized by the ions of elements below it. And you don't have to memorize the activity series, but you have to know the general order of elements on the activity series, and I'll explain exactly what I mean there. So if you take a look, here's the activity series. Now it doesn't list absolutely every metal, but for most of the common metals it does list them. What you'll see is at the very bottom you got yourself gold. Now if you know anything about gold, you know that it is one of the most unreactive elements out there. Sometimes we call these the noble metals. It's gold and platinum. And down here silver is not too far away. So these are the unreactive. So on the activity series they sit at the bottom, which makes sense. And then up here you have group 1 ions, lithium, or group 1 metals, lithium, potassium. If you recall, these are actually very reactive. So at the top you have very active metals, at the bottom not so active. And so these can always replace the ones at the bottom. And I'll show you what that looks like in a reaction. So we'll kind of finish up with this example. And this example says, which of the following metals will be oxidized by lead 2 nitrate? And the idea here is, why don't we explain this as a little parable. So we got zinc and lead 2 nitrate. So we'll think of this as there's a party in the beaker. So zinc, so actually what happens is both zinc and lead are invited to the party in the beaker. Now if you are visualizing the party in the beaker, here's a beaker, and the party is going on inside. And let me show you what the party looks like. It kind of looks like this. This is where the party is going on. So what you have is the lead came to the party, and so did zinc. And so zinc, actually being by itself, kind of sits down on the couch and just kind of looking around, and along comes lead with a few nitrates. And zinc says to himself, those are some good-looking nitrates. Wouldn't I want me a few nitrates? And so now zinc takes a look at the activity series and asks itself, am I more active than lead? Can I beat back and take lead's nitrates? So if you take a look at the activity series, zinc indeed is above lead on the activity series. And let's flip back here. So here is zinc, and here is lead. Zinc is above, zinc is more active, so zinc will be able to beat back lead and steal its nitrates. So zinc will be, there will be a reaction in this case. If we analyze the same thing with copper, so now we've got copper and lead 2 nitrate. So copper is actually sitting on the couch, along comes lead, and copper wants to beat back lead and take its nitrates. So if you take a look at the activity series, is copper above lead? And actually copper is below lead. Since copper is below lead, it is less active than lead. It will not be able to steal its nitrates. So that in this case you actually will have no reaction. So copper will not be able to be oxidized by lead. And finally, if you take a look at iron, the question again is iron above lead on the activity series? And if you take a look, lead is down here and iron is above lead. So iron can replace lead, so iron will be oxidized by lead. So this one is a go. Alright, that concludes this third lesson over oxidation reduction reactions.